So my 7th grade son said that they just learned this yesterday in math class, so you probably learned this in the past too. Let's review. I've got a pentagon up here, a 5-sided shape. It's got 5 angles on the inside. It has 5 corners, 5 vertices, and how many triangles can we make out of this? So what we do is we pick one vertex and we start connecting to another vertex so that we split it into triangles. And you can see that I have 1, 2, 3 triangles that I've made here. And why would you do that? Because if you were talking about those 5 angles in the pentagon, well, that would be the same as adding up the 3 angles in each triangle. And each triangle is 180 degrees. So if we take 3 times 180, we get 540 degrees. And that is the sum of the 5 interior angle measures for a convex pentagon. Let's look at the hexagon. Pick a vertex, connect, connect, connect. How many triangles? 1, 2, 3, 4 triangles. There's 6 interior angles, 6 vertices, and 4 triangles. 4 times 180 is 720. So those 6 angles on the inside of any convex hexagon would add up to 720 degrees. And here's an octagon. Maybe you can predict. I know that there's 8 interior angles, 8 vertices, and if I pick one of them and start making triangles, how many triangles can I make? 1, 2, 3, 4, 5, 6. Do you see the pattern? And 6 triangles at 180 degrees each would make a total of 1,440 degrees total for all 8 of those angles added together. I'm sure you see the pattern for number of interior angles and number of vertices. We could even do in general, if there were n sides, there would be n interior angles and n vertices. What was the pattern for number of triangles? It's always less than the number of sides. And so, like a square, you could split that into 2 triangles by connecting the vertices. A heptagon, we'd be able to make 5 triangles. An n-gon, just 2 less than however many sides there were. And when you take the number of triangles times 180, you get the total of all of those interior angle measures added together. And on this one, I guess I would just take the number of triangles that I made times 180. So that's a little formula for finding the sum of all the interior angles in a polygon. This new chapter starts out with polygons. We're finally trusting you with more than 3 sides on your polygon. And we'll be focusing mostly on 4-sided polygons, quadrilaterals this chapter. But here's that formula, and here's what it technically stands for. The sum, if you add up all of the interior angles, has to be a convex polygon. If you have a concave polygon, things are going to get weird. So, and we're going to use n for the number of sides, and the formula is n minus 2 times 180. That gives you the sum of all of the interior angles. Do you remember the word regular polygon? That's where all the sides and all the angles are congruent. And in particular, we're studying the angles today, so the sum of the interior angles of a regular pentagon. Honestly, the word regular doesn't make a difference there, other than we know that it's convex then. But the sum of the interior angles just always follows that formula n minus 2 times 180. So in this case, we would take n minus 2, 5 minus 2 would be 3, and 3 times 180 is 540 degrees. So I know that those 5 angles add up to 540 degrees total. Now this next question is not something you can always do. Not always are all 5 of those angles the same, but in a regular polygon they would be. So that 540 degrees is actually split evenly amongst those 5 angles since they're all congruent. So we could actually just take that total divided by 5, and that's going to give us the measure of each of those angles. And so I guess if you wanted to make a formula out of that, you would say that the measure of each angle in a regular polygon would follow that same formula at first, n minus 2 times 180. That would give us the total. But then once you have the total, you divide by how many angles there are, which is n. So this is going to be new to you. We're going to talk about the exterior angles. We talked about that with triangles a couple times, but the exterior angles of a polygon kind of looks like a pinwheel. You just extend all of those sides out, and all of those little green angles are the exterior angles. And I wonder what those would add up to. Just like we used the little triangle trick on the last one, let's look at this animation and see if you can figure out the answer. So we have three different types of polygons represented here, and it has those sides extended so you can see the outside angles, the exterior angles. And those angles aren't changing size, but they are like shrinking up that shape. Do you see what all the angles add up to once that's all the way shrunk down? On that triangle, they added up to a full circle, and on the pentagon, a full circle. And on that hexagon, the exterior angles added up to that full circle. How many degrees are in a full circle? Well, here's the formula. No matter what convex polygon, the exterior angles always add up to 360 degrees. That full circles, and so you don't even need to do any n-2 or anything. The answer, the formula, is just straight up 360 degrees for the sum of the exterior angles of a convex polygon. So if I give you this octagon and I ask you what is the sum of all of those exterior green angles, you would automatically just say 360 degrees. Not much work at all to do there. The sum of the exteriors is 360 degrees. Let's do some examples, and if you want to include an example in your notes, you sure could. This first one is giving us 4 out of the 5 angles in this pentagon, and they're wanting us to find that top angle, the measure of that top angle. And so our strategy here would be, well, I bet I could tell you how much all 5 of those angles add up to. They're interior angles, so I would just do 5 minus 2 times 180. And you might accidentally start memorizing some of these. So pentagon has interior angles that add up to 540 degrees. Well, how much do we have so far? Let's figure out what all of these add up to. And I think those add up to 450 degrees so far. So then the question is, how much would be left for the missing angle? All we have to do is take 540 and subtract off what's been used up already. And we get that that's a 90-degree angle up top there. The next example, I have a regular dodecagon, which means all of the angles are congruent. And that means I could find the measure of each of them, even though none of them are labeled. Dodecagons have 12 sides, so I'm going to do 12 minus 2. That would tell me there's 10 triangles that I could make, times 180. And so those 12 angles in there should add up to a total of 1,800 degrees. Now, since they're all the same, we can take that 1,800 degrees and divide equally by 12. This would only work for a regular dodecagon because all of the angles are the same. It's split equally. And that comes out to 150 degrees each. Every single angle in there is 150 degrees. I'm seeing this next example is obviously talking about the exterior angles. Looks like that pinwheel. And it even tells me that this is a regular octagon. So if it asks me for the sum of all of those exterior angles, what's the sum of all 8 of those angles? 360. That's the formula for finding the sum of the exterior angles. Now I can go one step further because this is a regular octagon. If all of these interior angles are the same, then all of the exterior angles must be the same. Do you believe that? See if you can convince yourself. So if those are all equal, and I know that the total is 360 degrees, and I want to split that amongst those 8 exterior angles, that tells me that each of those exterior angles is 45 degrees each. And so if you wanted a formula for each exterior angle in a regular polygon, I guess it would just be 360 degrees divided by n, right? N tells us how many exterior angles are going to share that 360 degrees. Now that's only if it's a regular polygon. If we look back to this first example, had we extended those exterior angles, some of them would match, but they aren't all going to be the same size, since those interior angles vary a little bit. These are the theorems from this section. The first one we've already talked about. It's just the formula, n minus 2 times 180. And the last one we talked about, the polygon exterior angles theorem, that the outside angles add up to 360. They put in an extra theorem. It's called a corollary because it goes on with 8.1. In the special case of a four-sided shape, 4 minus 2 times 180 is 360, but that's a good one just to have memorized in your head. You guys know about squares and rectangles and stuff. They all have 90s, and 9 times 4 is 360. So you kind of already knew that the interior angles of a quadrilateral would be 360 altogether. And that's the first section, just studying the angles inside and outside of convex polygons.